Okay, so today we're gonna learn the Kosaraju algorithm. So what this algorithm is used for, it is used to find the shortest path in a graph. So it is Kosaraju algorithm. Okay, so it is used to find the shortest connected components in the graph. So let me take an example and explain you a bit clearly. So let's say we have a graph like this. Let me draw a graph first and then I will explain you what is all going on. Okay, so we have a graph here. Now I want to find how many connected components are there in the graph. So what is a connected component? A connected component is a subgraph in a graph in which every vertex has a path to the other vertex. So let's say this is a one connected component, let's say A. This is the second connected component, let's say B, and this is the third connected component, let's say C in this graph. Now, if we see the first connected component, that is A, we have a path from 1 to 0. We have a path from 1 to 2 that goes from 1 to 0 and then from 0 to 2. And we have a path from 0 to 2 and also from 0 to 1. We have a path from 2 to 1 and from 2 to 0. But let me include this vertex also, that is 3 vertex also in this connected component. So we have a path from 1 to 3. Yes, we have a path, but from 3 I cannot move back to 1. So we have no path from 3 to 1, nor we have a path from 3 to 2. So 3 cannot be in this connected component. Okay, so there are 3 connected components in this graph, that is A, B that contains only a single vertex, that is 3, and C that is also a single vertex, 4. So my task here is to find these connected components in the graph. So for this we will be using the Kosaraju algorithm. So let me first tell you the intuition behind this. So if I run a DFS over this graph, what I got? Let me run this and let's see what happens if I run a DFS over this graph. So let me start the DFS traversal from the node 1. So if I am at node 1, I will start my DFS traversal. 1 is connected to 0, so 1 will call the DFS of 0. Let's say 0 calls the DFS of 2 first. So it will call DFS of 2 first. Okay. Now 2 is connected to 1, but 1 is the parent of 2. So 2 will backtrack. Okay. Now DFS of 0 will move to DFS of 3. DFS of 3 is connected to 4, so it will go to DFS of 4. And 4 is not connected to anyone, so it will backtrack, and 3 will backtrack, and 0 will backtrack. So if I run the algorithm, the DFS algorithm from the 1, then I got 1, 0 and 2, and then I go to again to 0 and then to 3 and then to 4. What if I record the finishing time of every node? So let's see. We first started from 1. Okay, so so its starting time is, let me show you the starting time and finishing time for each of the vertices. So its starting time is 1. Then I move to 0 so its starting time is 2. Then I move to 2, so its starting time is 3. Now I backtrack from 2 to 0, so its finishing time is 4. Now 0 moves to 3, so 3's starting time is 5. And then we move to 4, so 4 starting time is 6. Now I will backtrack to 3, so its finishing time is 7. And then 3 finishes, so it will be 8. Then 0 finishes, then it will be 9. And at last 1 finishes. So if I store the vertices in a stack in the order of their finishing time. So firstly, we will be storing 2 here because 2 was the first vertex that was finished. Then we will store the 4. Okay, then I should pop I should push 4 here. Then we will be pushing 3 here. Okay, and then 0 and then 1. Okay, so now I have pushed the vertices in the order of their finishing time in a stack. Now what I have to do here, I have to reverse the edges in this graph. So what I will get here is that 1 0 3. So when I am reversing the edges of this graph, it simply means that I am transposing this graph. And what if you have given the adjacency matrix form, then you have to transpose that adjacency matrix only. So there will be an edge from 1 to 2 when I reverse the edge from 2 to 1, and this edge will be reversed also, and this edge will be reversed also, reversing this edge also and reversing this edge. Now I have reversed the edges, so what I have to do now, I have to just pop the element from the stack. And let me also take a visited array that will tell me what are the elements that are visited. So its size will be of the number of vertices. So here it will be 0 1 2 3 4. Okay, so now I have popped 1 from the stack, so I will make it as true on the 1 index so that I can see that 1 is now visited. So if I take 1 now I will run DFS over this transposed graph taking 1 as the root. So if I take 1 as the root and run the DFS, what I will get, I will go to 2. Now I will run DFS of 2, and 2 will go to 0. I will run DFS of 0, and 0 will again go to 1. And while going to 2 and 0, I will make them as visited. Now 0 will backtrack and 2 will backtrack, and this DFS will be called off. So while calling these DFS, I will just print the elements in the order which I have called. So I will first print 1, then I will print 2, and then I will print 0. And this will be my first connected component that I will get. Now again I will see another element from the top of the stack, that is 0. But what I see here is that 0 is already visited. 0 is already visited, so I will not make a DFS call on 0. Again, I will just pop the element from the stack, that is 3. Here 3 is not visited now. So what I will do here, I will just call the DFS of 3. So when DFS of 3 will be called, it is just connected to 0, and what I can see from here clearly is that 0 is already visited. So I will not call the DFS on 0 here. So I get only 3 from here. So that is my second connected component. Now uh, I will just make this as true, 3 as visited. I will come to 4, 4 is not visited yet. So what I will do, I will just call the DFS of 4. So DFS, by calling the DFS of 4, we see that it is connected to 3, but 3 has been already visited, so it will not call any further vertex in the DFS, and we will print 4 as our third connected component. Okay, so we will print 4 as our third connected component. Now the stack has one more element, that is 2, but when I pop out 2, I see that it is already visited. Now stack will be all empty. When the stack will be empty, I move out of the loop, and I can see here that I have got all my 3 connected components. So what we have done here in this algorithm is, let me write it in steps. So firstly, what we have done here is we have run the DFS on G, graph G, and stored vertices in order of finish time in stack. Second, what I have done is find G transpose, and third, run DFS on G transpose. So these are the 3 steps that I have done here, and finded the connected components in a graph by using the Kosaraju algorithm. So hope you have understand this algorithm. If you have any doubts, you can comment down this video, and I will try my best to resolve your queries. Thank you.